Maciej Kańduła is certainly not a stranger to the CAMDA community. So he's from Buku University in Vienna, and he's going to present a systematic analysis of multiple cancer studies within a novel enhanced framework for semantic data integration. Maciej.
Hi, thank you for the introduction. Hi, welcome to my talk on data integration of cancer datasets. My name is Maciej Kańduła, and this work was performed together with Ilyan Mikhailov and Dimitar Vasilev from the Sofia University in Bulgaria. Thank you for this opportunity, and I hope you'll enjoy my talk. This works nice. Okay, so first we'll be talking about data integration, open issues basically, and then I will be showing our system that should tackle these issues, and I will then at the end basically briefly summarize what we developed. So data integration. Currently we have a large amount of matched samples available for cancer data sets, not only for cancer, but this is the topic of my talk here. And we have heterogeneous data coming from different data sources. So we have microarray data, RNA-seq, proteomics, copy number data. But apart from this, we also have information coming from mined texts, for example, and from clinical information. So there's actually surprisingly little integrative research being performed. Here in this plot, you can see the papers citing TCGA dataset, either expression, RNA-seq here in this case, or copy number data. And this blue line at the bottom are actually papers that actually use both of these datasets in a joint fashion. So as you can see, this is really a low number. And there is, however, a great interest in developing systems that would actually use all these different data sources. And this is here a slide from a keynote from Monday, and he was actually talking about this as well. So how to make sense out of all this data, how to actually solve the puzzle. This is a problem, or for us maybe an opportunity, and it's recognized in the bioinformatics community, as you can see here. Okay, so data integration might actually, or does actually also mean knowledge management. By what I mean that we need to store this data somehow, but also make it accessible and actually usable somehow. And it's not actually, for example, simple to store relations of data that's of different structure. And all these are well-recognized challenges in bioinformatics. I have citations for these. Data integration can be performed in a vertical fashion or in a horizontal fashion. And what I mean by this here is that we have information for one data source. We can have information coming from different patients. So we will have clinical data for patient 1, for patient 2, for patient 3. Now the question could be how to integrate this information coming from all these patients. And also, next question is how to actually integrate information from different technologies for this one specific patient here. And then the final question is how to actually combine both of these approaches. And this is what we try to tackle with our system for data integration. So this looks like quite a complicated pipeline. All the red text and rosy boxes are things that we added since last year because this prototype of the system was already presented last year by Dimitar. So now we focused on the new data sources, data sets, so the new cancers. Last year it was neuroblastoma and metabric breast cancer data. At this time we have, as discussed already, breast cancer, lungs, and kidney cancer data. And we have new data sources. So we further developed our system to actually take in all these additional data sources and the new cancers, we automated the pipeline so you can actually retrieve any information from the TCGA that's available there. And after you retrieve the information, the data is normalized, pre-processed, and put into a database. And within this database, we can then use both the molecular information that we put in and external information here in a loop, basically, coming from UniProt, Ensemble, or gene ontology terms, for example, and try to actually find relations in the data. So here we perform a horizontal data integration, as I explained, so you have different patients and data for them, and then in a linked next database, we basically vertically integrate the information as well, some from different data sources here. I mean, the steps are maybe not as important in details for the moment. But what we can do next is just come up with some application of this data that's now readily available for us. So our first, the application that I'm showing here is actually for survival time prediction. And what we do is first we use the clinical information, and this is actually an example from last year. So there was tumor stage available, tumor size, age at diagnosis. And what we do here is based on a principle of superposition, we actually put the features in certain order which contains more information with regard to basically highest biological sense. So we actually go through different clinical features, alone as well, but also in different combinations, and we look at which combination or feature alone yields the most information for survival time prediction. Yes, so as I said, these are features that were available last year, and here actually, so the order that we use actually also biologically makes sense because tumor stage 1 versus tumor stage 4 will actually make a huge difference between the information in the patients. Yeah, so we first select, using the k-nearest neighbors approach, using this clinical feature, this integrated clinical feature, we select for the patient of interest, we select neighbors of the patient basically in the data. So patients that have clinical information that's closely related to this one patient. And when we have the patient's neighbor basically, we can build a network of relations here. So so nodes here are the patients. We have our patient of interest here, the studied patient, and the edges here, the strength of the relation between patients is based both on the clinical information, but also molecular data, and the data linked from external data sources. So here, UniProt, Ensemble, and gene terms, gene ontology terms, sorry. Yes. And we can then use information from the other patients to actually figure out what the survival time of the studied patient will be. And this is what we do here. And even if you don't see the exact numbers, I will tell you actually what we see here. So on the left side, you have different machine learning methods that should predict survival time of the patients. And to the right, I'm just showing which sources of information we are using for this particular predictions. So this is the R squared here, basically in the first column. And starting from the bottom, this is now, these are results generated, so survival time predicted, not using our integrated clinical feature and not using our relational network. And if you compare this to results where we use the combined clinical feature, actually they don't really change that much. But when you add the relational network, then you get quite an increase in performance here. And when you actually, with the relational network, additionally also use the combined clinical feature, then we arrive at the best results here. And of course, for different machine learning methods, the results will differ a bit. So yeah, so here, yeah. And these results are shown for the Metabrick data set from last year. So now we actually, and this is only on one cancer here, just to be clear. And what we do here in these results, we actually integrate information across different cancers. So we actually combine information coming from these 3 cancers from this year. And here, we actually extended our framework to also add additional machine learning models, machine learning methods. And here, I mean, so we test how the results would look like using only a specific clinical feature. And here they are different here because this is a different data set. So TCGA would usually actually provide all of these. Then TICF would be our combined feature here. And TICF plus RNA is basically using molecular information as well. And as you can see, for I would say most of the methods, we can outperform the other approaches when we use both the clinical, both the joint clinical feature and molecular data. But it's not always the case. So for example, for the lasso method, actually the clinical feature alone was better than when using RNA-seq additionally. And for example, for K-neighbors regressor, the results were actually better when not using RNA-seq and our combined clinical feature. So this nicely shows that data integration might not be always helpful. But of course, you could say, okay, I can actually use the best one here, and actually the improvement is not as huge. But yes, it always depends what kind of method you use, and this is for a specific data set, so on a different data set, this might look a bit different. And these are very fresh results, and we are still working on this. Okay, so just to sum up, we have developed an integrative system where integration facilitates ease of access to the data, facilitates finding relations between different data sources, between different patients even. And we find this to be extremely beneficial on its own, but so far on this one example application that I have shown, we show that integration can be beneficial for specific tasks too. And what we are doing now is considering other applications. So we could, for example, stratify the patients into groups and get different hazard ratios for them, for example, to find the best treatment. And we are also working on adding more cancers, actually really including all the other molecular data types in our final analysis. And we are working on also a complex cross-validation pipeline, where we also add more machine learning models. Okay, thank you very much for your attention.
Thank you, Maciej. Any questions?
Okay. First, the comment, I like this approach very much, but
Thank you.
the results are incredibly good, with the stress on the incredibly. I'm afraid that you have some information leakage due to your data integration before the cross-validation, because this is simply, it looks like they are problem solved, yes? We know everything about survival. Variance explained 99%. So I would commend that you should really take care about the cross-validation to include it as early as possible, because otherwise it might be that you have some information leak in your methodology. Apart of that, I think that it's very nice framework, and it really looks very interesting, but be careful.
Yeah, thank you very much for the comment. Yes, I agree, and that's why now we actually put a lot of work into actually making the cross-validation, as you suggest as well, work good for this. Yeah, thank you.
Thank you for the talk. I just have a question. If you take just all clinical data, or you do some curation, some selection, because I mean this clinical data in TCGA can be sometimes very noisy, you know, and I wonder if you do some pre-selection of this data.
So we actually select based on how much information there is available in external data sources. So the more something is confirmed, the stronger the link will be.
Any other questions? If not, I'd just like to say that I forgot to mention yesterday that behind the challenges, a lot of work, heavy liftings were actually done by Maciej. I don't know if everybody in the community actually know. He put a lot of effort putting the data together so we can actually have these challenges. So thank you, Maciej.
Thanks.